The most distant human-made object ever launched is NASA's Voyager 1 spacecraft, an engineering marvel that has ventured farther than any probe in history, now floating through interstellar space over 4.5 decades since its launch. Imagine the audacity of launching a spacecraft in 1977 and having it still function today, exploring regions of space no one could have predicted it would reach, operating well beyond its intended 4-year lifespan. This is the astonishing reality of a mission that began as a brief planetary tour and has evolved into humanity's longest and most daring journey into the cosmos. What's even more incredible is that Voyager 1, billions of miles from its launch point, continues to beam back data using technology older than a cassette player, relying on computing systems with less memory than a digital wristwatch. The fact that it can still communicate with Earth, despite its transmitter using only about 20 watts of power, barely more than a household light bulb, is a testament to the ingenuity of NASA's engineers in the 1970s. And just recently, Voyager 1 sent back a data packet that shook the scientific community to its core, a new finding from the far reaches of interstellar space, capturing the imagination of scientists and the public alike, and raising profound questions about the universe and our place in it. The story of Voyager 1 begins with a remarkable alignment of the planets that occurs only once every 176 years, a rare celestial configuration that was first identified by Gary Flandreau of NASA's Jet Propulsion Laboratory. With just a pencil and a slide rule, Flandreau mapped out a revolutionary route for a spacecraft to use gravity assists from Jupiter, Saturn, Uranus, and Neptune in a chain reaction that would sling it farther and faster than previously possible. This celestial necklace of planets offered a unique chance to reach the outer solar system using the gravitational fields of the gas giants to boost a spacecraft's speed, like being pulled by invisible ropes. NASA seized the opportunity, knowing it would not come again in this generation, and in the summer of 1977, just 15 days apart, it launched two nearly identical spacecraft, Voyager 1 and Voyager 2. Designed to take advantage of the planetary alignment, these twin probes were initially tasked with a grand tour of the outer planets, a mission expected to last just a few years. But what unfolded was nothing short of legendary. Not only did they complete their initial mission, they far exceeded expectations, journeying into the unknown and transmitting data that continues to reshape our understanding of the universe. From the beginning, the Voyagers amazed scientists. Voyager 1 provided humanity with breathtaking close-ups of Jupiter's swirling storms and its volcanic moon Io, where active eruptions stunned observers. Saturn revealed its majestic rings in exquisite detail, along with its moon Titan, shrouded in an orange haze that hinted at a dense atmosphere. Meanwhile, Voyager 2 became the first and only spacecraft to visit Uranus in 1986 and Neptune in 1989, revealing turquoise worlds with dynamic weather systems, mysterious magnetic fields, and moons that had never before been seen. These discoveries redefined what scientists believed was possible in the outer solar system. Icy moons showed evidence of geologic activity, subsurface oceans, and complex histories, challenging the view that distant worlds were lifeless, inert spheres. More than 14 billion kilometers from Earth, these Volkswagen Beetle-sized spacecraft pushed the limits of endurance and reliability. With just 69 kilobytes of memory, less than a single image file on a modern phone, the onboard computers had to autonomously handle tasks like trajectory correction, instrument management, and data storage. The spacecraft recorded information on 8-track tape recorders and used their 12-foot satellite dishes to transmit signals across the vast emptiness of space at the speed of light. Yet each day, they moved farther from Earth by another 3 or 4 light seconds, making communication increasingly difficult and time-consuming. Despite the technical limitations, both Voyagers continued to function. They survived the perils of the asteroid belt, powered by radioisotope thermoelectric generators that used the heat of decaying plutonium to generate electricity. Their longevity allowed them to cross beyond the orbits of Pluto and approach the boundary of the heliosphere, the vast bubble of magnetic fields and charged particles generated by the sun that encompasses our solar system. Scientists had long theorized that this heliopause marked the transition into interstellar space, the region beyond the influence of the solar wind and into the environment shaped by other stars. But precisely where this boundary lay, and what lay beyond it, remained a mystery. It was estimated that the heliopause sat around 50 astronomical units, AU from Earth, and as the spacecraft approached this region, NASA continued funding the mission in hopes of making a once-in-a-lifetime crossing. But the transition proved less clear-cut than expected. Voyager 1 sensors were calibrated to detect changes in cosmic ray density and magnetic field orientation, signatures that were supposed to clearly distinguish the solar system from the interstellar medium. Surprisingly, as the probe moved past $120 Australian, scientists observed a sudden spike in plasma density, a hallmark of interstellar space, but without the anticipated shift in magnetic field direction. This anomaly puzzled researchers. If Voyager 1 had truly exited the heliosphere, why hadn't the magnetic field changed? On August 25, 2012, NASA officially confirmed that Voyager 1 had entered interstellar space based on plasma measurements that showed a dramatic increase in electron density. Yet the absence of a shift in magnetic field lines defied expectations. One theory proposed that the interstellar magnetic field might be aligned in an unusually smooth way with the solar field, creating a gradual rather than abrupt transition. If true, it meant that the forces sculpting our solar neighborhood were more nuanced than imagined. Others hypothesized that the heliopause wasn't a sharp boundary at all, but rather a fuzzy, turbulent region of complex interactions between solar and galactic forces. Either way, Voyager 1 had achieved a milestone no other human object had reached. It was now traveling through the space between the stars, offering the first direct measurements of this uncharted territory. And what it found was nothing like the uniform, static void once imagined by astronomers. Instead, the interstellar medium appeared dynamic and varied. Plasma readings showed dramatic fluctuations, with Voyager 1 encountering regions of varying density, temperature, and pressure. Some areas were dense and hot, others were sparse and cold. These fluctuations hinted at a chaotic environment shaped by ancient supernovae, stellar winds, and long-forgotten cosmic collisions. Scientists began to refer to these features as plasma clouds, distinct pockets of interstellar matter that seemed to align with known remnants of supernova explosions. It was as if Voyager 1 had wandered into a cosmic graveyard, passing through the ashes of long-dead stars. Each plasma cloud carried unique signatures that might reveal clues about events that occurred millions of years ago, well before the birth of our solar system. The notion that the interstellar medium contained such rich structure was revolutionary. Prior models had assumed a smoother, more homogeneous field sculpted by the combined influence of stars over vast timescales. But Voyager 1's instruments told a different story. These pockets of high-energy particles and dense plasma pointed to a more turbulent galactic neighborhood, suggesting that space was far more alive and complex than previously understood. Some scientists proposed that these plasma regions might be shaped by shock waves from ancient explosions or pressure differences caused by variations in the interstellar wind. Others believed they could be evidence of larger galactic processes that subtly influence our solar system's orbit through the Milky Way. Whatever their origin, these structures fundamentally challenged how we perceive space beyond the sun's reach. The data from Voyager 1 continues to confound and inspire. It paints a picture of a galactic ocean in constant motion, filled with eddies and currents, rather than a calm and featureless vacuum. The probe's long journey, now approaching $160 from Earth, is a testament to human perseverance and scientific ambition. Operating on dwindling power reserves and aging systems, Voyager 1 remains a solitary envoy in a region never touched by humanity. Every signal it sends, though faint and delayed by over 20 hours of travel time, carries priceless information from the frontier of the known. And still, it surprises. Just recently, the spacecraft detected a new spike in plasma wave activity, possibly indicating another encounter with a dense cloud of interstellar material. These readings are being analyzed with great care, as they might help define the shape and structure of the transition zone between our solar system and the wider galaxy. Meanwhile, Voyager 2, though slightly behind its sibling, has also crossed into interstellar space and continues to transmit valuable data from a different path, offering a comparative look at how the solar system interacts with its surroundings in multiple directions. The twin probes have become more than just scientific instruments. They are symbols of humanity's desire to reach beyond the horizon, to explore not just for discovery's sake, but to understand our origins, our future, and our place in the cosmos. Long after they fall silent, they will continue to drift outward, carrying the golden records, time capsules of Earth's culture and sounds, on a billion-year journey through the stars. They may someday be found by another civilization, or perhaps drift forever, unnoticed, relics of a curious and inventive species that once looked to the skies and dared to dream. Until then, they remain our most distant ambassadors, whispering secrets of the universe from the silent depths of space, reshaping our understanding with every byte of data. And so, with each passing day, Voyager 1 travels farther into the unknown, proving that even the oldest technology can achieve greatness, and that the human spirit, encoded in metal and guided by vision, can touch the stars. Even now, nearly 5 decades after its launch, Voyager 1 continues to defy expectations. NASA engineers, faced with a spacecraft operating far beyond its intended lifespan, have become adept at finding ingenious workarounds to keep it functional. They have reprogrammed its software remotely, switched to backup systems, and rerouted power from non-essential instruments in a delicate balancing act of preservation and science. Every command takes nearly a full day to travel to the spacecraft and back, and yet the team persists, driven by the rare opportunity to receive data from a realm no other mission can reach. In 2024,